Okay, folks, stick with it. We're on physics. We're looking at the first physics question in your Year 9 exam, and we're being asked to identify, using the letters on this diagram, the wavelength. So fact, remember, the wavelength is the distance between equal disturbances. R is the correct label for one wavelength. Q is wrong because this wave is going up here and down there, so it's not Q, and S and P are related to the height of the waves and not to how spread apart their peaks or troughs are. The amplitude is the height of the wave above the line of symmetry through the middle. S is the correct box to tick for the amplitude. Okay, if you've got these wrong, make sure you've memorized the definition of wavelength and amplitude and can identify them on a diagram. Okay, you've been given an equation here. The period equals 1 divided by the frequency. So on your calculator, you're going to plug in those numbers. The period is 1 divided by the frequency, which is here, 0.2 hertz, and that gives you an answer of 5 seconds. That answer means that for this wave with this frequency, one complete wave will take 5 seconds of time. Part D, the frequency of the waves is increased. The speed of the wave stays the same. What happens to the wavelength? We might recall that there's an equation that links these three things. The speed of a wave is the frequency times by the wavelength. So if V stays the same and F gets bigger, the wavelength has to get smaller. If you're ever completely stuck on this, you could always put some numbers in. So for example, 4 equals 1 times 4. Speed stays the same. The frequency is increased. The wavelength has to decrease as well. Any numbers would prove that point for you. Okay, to get the next question here, we want to be looking in detail at the information about this investigation. It says a student investigates how the speed of water waves is affected by the depth of the water. So we're saying, I want to change the depth and see if it changes the speed. I'm going to change the depth. I'm going to measure the speed, and here's some apparatus. The student lifted one end of the tray and dropped it. This made a wave which travelled the length of the tray. The student measured the length of the tray. What else does the student need to measure in order to calculate the speed? So perhaps you recall from maths that speed is distance divided by time. If I know the length of the tray, I know the distance, so I also need to measure the time for the wave to travel the length of the tray. Part F is asking you to spot which is the independent variable. Remember, you investigate the independent variable, and the independent variable is the thing that we would change each time. In this case, it's the depth of the water. Okay, the next part is giving you a graph to interpret. Whenever you get a graph, always think whatever's on this axis is affecting the thing on this axis, and we're looking for a pattern or a trend. So you can see from this graph here that as the depth of the water gets bigger, the speed of the waves also gets bigger. So we can put that into a sentence and say, as the depth increases, the speed also increases. There's only one mark, so one sentence will do. If there was a second mark for this graph, I might say that the line appears to be curving, so the rate of change of speed, or the rate of the increase of the speed, is getting less and less and less. In other words, as depth gets bigger and bigger and bigger, it has less and less and less of an effect, although it will keep going up. Deeper water, faster waves. What was the speed of a wave when the depth of the water was 2.5 centimeters? To answer this question, I should go to 2.5 centimeters, which is here. I'm going to draw a line up to the line of best fit. I'm going to draw a line across to this axis. I'm going to read off this value, and the correct answer is 0.49 meters per second. We should be getting this exactly right. It's right on the line. Okay, every 2 squares, 0.4, 0.5, 0.4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each little square is 0.01. Okay, question 8 is about the electromagnetic spectrum. I've got a diagram showing the position of 3 types of wave in the electromagnetic spectrum. Which position shows where visible light is? So think of your order here. Maybe you've listened to the electromagnetic spectrum song and you've learnt it, but I'd be thinking to myself, well, I know that D is going to be gamma rays, and then here, radio waves, microwaves, infrared radiation, visible light. So visible light is at position C. Okay, a good way to remember this is that the R for radio waves is on the same side of visible light as the R for infrared, and visible light would be red, orange, yellow, green, blue, indigo, violet. Ultraviolet is past violet. Okay, so there's a few little tricks to try and remember the order of waves in the electromagnetic spectrum. One of the statements about electromagnetic waves is correct. I'm going to take each one in turn and see if I can decide if it's definitely right or wrong. Radio waves have a higher frequency than X-rays. Now I know that this end is the highest frequency, and this end is the lowest frequency, and that's because these waves all travel at the same speed. Gamma rays have the smallest wavelength, and radio waves have the longest wavelength. So we need to know those facts to answer this question. So do radio waves have a higher frequency than X-rays? No, they don't. Do radio waves have a longer wavelength than ultraviolet? The wavelength is getting shorter this way, smaller. This one seems to be true, but I'm not going to commit just yet. I'm just going to check the others. X-rays have a longer wavelength than radio waves. No, that's not right. X-rays travel faster through the air than ultraviolet. That's definitely wrong, because all of the electromagnetic waves travel at the same speed. Part C, a possible danger of exposing your skin to ultraviolet radiation. Okay, we need to be specific here and remember that a bigger dose of ultraviolet radiation increases your risk of skin cancer. Don't just write cancer, it needs to be specific to the question, increased risk of skin cancer. Okay folks, we're looking at some data here. It's giving us information about the dose of radiation when you have X-rays taken of different parts of your body. So you can see for different parts of the body, when you have an X-ray, you receive a different dose. So that's the amount of radiation your body has received. We've got a fact here the risk of an X-ray causing cancer is about 1 in 20,000 for each millisievert of radiation received. Now there's two things we can do here. We've got this statement, so we must do that, and we need to compare the risk of developing cancer from having an X-ray of the upper digestive system to having an X-ray of your chest. Now you can see just by looking that the risk is going to be lower for the chest. So for 1 mark here, we can comment that the risk is higher having an X-ray taken of your upper digestive system than it is having an X-ray of your chest. Okay, so you can see here my answer says the risk of developing cancer is higher when you have an X-ray of your upper digestive system. So I've stated a fact, I've got 1 out of the 2 marks, but I haven't used the data, so I can't access the second mark yet. Now if I'm looking at these two numbers and I need to compare, I might say how many times more is this dose compared to this dose? In other words, how many times does 0.1 go into 5? And the answer is 50. So I could add a second point here. I've used the data. The risk of developing cancer is higher when you have an X-ray of your upper digestive system by a factor of 50. It's 50 times more risky to have an upper digestive system X-ray than a chest X-ray. Okay, an alternative approach would be to use this fact that the risk is 1 in 20,000 for each millisievert. So the chest, which is only 0.1 millisieverts, is going to be 10 times less. So the chest risk is going to be 1 in 200,000. And the upper digestive system is going to be 5 times more likely. 20,000 divided by 5 gives me a risk of 1 in 4,000. So this would be an alternative way to use the data to compare the risk. Both are showing that the upper digestive system X-ray is 50 times more risky for your risk of developing cancer as a result of the X-ray. But remember, an X-ray's job is to help diagnose problems. It will probably always be more valuable to know what the problem is by having an X-ray than the risk of developing cancer because of having the X-ray. Okay, last question in physics. We're being asked to describe, so what are the differences between longitudinal and transverse? For both types of waves, we need to show that we appreciate that there is an oscillation that causes the wave. And that all waves transfer energy. So when I describe the longitudinal and transverse waves, I need to say that the oscillation that causes the wave relative to the energy transfer of the wave. So for a transverse wave, we need to show we understand that the oscillation, the vibration that causes the wave, is at right angles to the energy transfer. We can say that the oscillation in a transverse wave is perpendicular to the direction of the energy transfer, whereas in a longitudinal wave, the oscillation is parallel to the direction of the energy transfer. Lots of people missed out this idea that a wave's direction is the direction of the energy that's being transferred from one place to another. Remember, there's no movement of material when waves are produced but energy is transferred. Final question, we're comparing radio waves to sound waves. Describe how radio waves are different from sound waves. I could answer this by making myself a little table over here. And I need to think of 3 facts to compare. So the radio waves are electromagnetic waves. That says it here. And I know that all electromagnetic waves are transverse, whereas sound waves are longitudinal. Okay, can you see that we're making pairs of facts in a comparison? We can say that radio waves can travel through a vacuum, whereas sound waves require a medium or particles, some stuff. Sound waves cannot travel through a vacuum. We can say that radio waves are faster than sound waves because all electromagnetic waves travel at the speed of light. Sound is much slower, about 1,000,000 times slower. The speed of sound in air is about 320 meters per second. The speed of light, and therefore radio waves, is 300 million meters per second. And finally, we might say that radio waves can have much greater frequencies than sound waves. But I think we've got our 3 comparisons here that makes our 3 marks for our final physics question.